Hello everyone. So from today onwards we'll be posting class 12 physics audiobooks. So this is the first time on YouTube that somebody is posting physics audiobook. So please give it a thumbs up and do subscribe for more content. Chapter 1: Electric Charges and Fields. Introduction. All of us have the experience of seeing a spark or hearing a crackle when we take off our synthetic clothes or sweater, particularly in dry weather. Have you ever tried to find any explanation for this phenomenon? Another common example of electric discharge is the lightning that we see in the sky during thunderstorms. We also experience a sensation of an electric shock either while opening the door of a car or holding the iron bar of a bus after sliding from our seat. The reason for these experiences is discharge of electric charges through our body, which were accumulated due to rubbing of insulating surface. You might have also heard that this is due to generation of static electricity. This is precisely the topic we are going to discuss in this and the next chapters. Static means anything that does not move or change with time. Electrostatics deal with the study of forces, fields, and potentials arising from static charges. 1.2 Electric charge. Historically, the credit of discovery of the fact that amber rubbed with wool or silk cloth attracts light objects goes to Thales of Miletus, Greece around 600 BC. The name electricity is coined from the Greek word electron, means amber. Many such pairs of materials were known which on rubbing could attract light objects like straw, pith balls, and bits of papers. It was observed that if two glass rods rubbed with wool or silk cloth are brought close to each other, they repel each other. The two strands of wool or two pieces of silk cloth with which the rods were rubbed also repel each other. However, the glass rods and wool attracted each other. Similarly, two plastic rods rubbed with cat's fur repelled each other but attracted the fur. On the other hand, the plastic rod attracts the glass rod and repels the silk or wool with which the glass rod is rubbed. The glass rod repels the fur. These seemingly simple facts were established from years of efforts and careful experiments and their analysis. It was concluded after many careful studies by different scientists that there were only two kinds of an entity, which is called the electric charge. We say that the bodies like glass or plastic rods, silk, fur, and pith balls are electrified. They acquire an electric charge on rubbing. There are two kinds of electrification, and we find that 1. Like charges repel, and 2. Unlike charges attract each other. The property which differentiates the two kinds of charges is called the polarity of charge. When a glass rod is rubbed with silk, the rod acquires one kind of charge and the silk acquires a second kind of charge. This is true for any pair of objects that are rubbed to be electrified. Now, if the electrified glass rod is brought in contact with the silk with which it was rubbed, then they no longer attract each other. They also do not attract or repel other light objects as they did on being electrified. Thus, the charges acquired after rubbing are lost when the charged bodies are brought in contact. What can you conclude from these observations? It just tells us that unlike charges acquired by the objects neutralize or nullify each other's effect. Therefore, the charges were named as positive and negative by the American scientist Benjamin Franklin. By convention, The charge on glass rod or cat's fur is called positive, and that on plastic rod or silk is termed negative. If an object possesses an electric charge, it is said to be electrified or charged. When it has no charge, it is said to be electrically neutral. A simple apparatus to detect charge on a body is the gold leaf electroscope, figure 1.2a. It consists of a vertical metal rod housed in box with two thin gold leaves attached to its bottom end. When a charged object touches the metal knob at the top of the rod, charge flows onto the leaves and they diverge. The degree of divergence is an indicator of the amount of charge. Try to understand why material bodies acquire charge. You know that all matter is made up of atoms and or molecules. Although normally the materials are electrically neutral, they do contain charges, but their charges are exactly balanced. Forces that hold the molecules together, forces that hold atoms together in a solid, the adhesive force of glue, forces associated with surface tension, all are basically electrical in nature, arising from the forces between charged particles. Thus, the electric force is all pervasive and it encompasses almost each and every field associated with our life. It is therefore essential that we learn more about such a force. To electrify a neutral body, we need to add or remove one kind of charge. When we say that a body is charged, we always refer to this excess charge or deficit of charge. In solids, some of the electrons being less tightly bound in the atom are the charges which are transferred from one body to the other. A body can thus be charged positively by losing some of its electrons. Similarly, a body can be charged negatively by gaining electrons. When we rub a glass rod with silk, some of the electrons from the rod are transferred to the silk cloth. Thus, the rod gets positively charged and the silk gets negatively charged. No new charge is created in the process of rubbing. Also, the number of electrons that are transferred is a very small fraction of the total number of electrons in the material body. 1.3 Conductors and insulators. Some substances readily allow passage of electricity through them, others do not. Those which allow electricity to pass through them easily are called conductors. They have electric charges, that is, electrons, that are comparatively free to move inside the material. Metals, human and animal bodies and earth are conductors. Most of the non-metals like glass, porcelain, plastic, nylon, wood offer high resistance to the passage of electricity through them. They are called insulators. Most substances fall into one of the two classes stated above. There is a third category called semiconductors which offer resistance to the movement of charges, which is intermediate between the conductors and insulators. When some charge is transferred into a conductor, it readily gets distributed over the entire surface of the conductor. In contrast, if some charge is put on an insulator, it stays at the place same. You will learn why this happened in the next chapter. This property of the materials tells you why a nylon or plastic comb gets electrified on combing dry hair or on rubbing, but a metal article like spoon does not. The charges on metal leak through our body to the ground as both are conductors of electricity. However, if a metal rod with a wooden or plastic handle is rubbed without touching its metal part, it shows signs of charging. 1.4 Basic properties of electric charge. We have seen that there are two types of charges, namely positive and negative, and their effects tend to cancel each other. Here we shall now describe some other properties of electric charge. If the sizes of charged bodies are very small as compared to the distances between them, we treat them as point charges. All the charged content of the body is assumed to be concentrated at one point in space. 1.4.1 Additivity of charges. We have not as yet given a quantitative definition of a charge. We shall follow it up in the next session. We shall tentatively assume that this can be done and proceed. If a system contains 2 point charges Q1 and Q2, the total charge of the system is obtained simply by adding algebraically Q1 and Q2, that is, charges add up like real numbers or they are scalars like the mass of a body. If a system contains n charges Q1, Q2, Q3, etc. Qn, then the total charge of the system is Q1 plus Q2 plus Q3 plus etc. plus Qn. Charge has magnitude but no direction, similar to mass. However, there is one difference between mass and charge. Mass of a body is always positive, whereas charge can be either positive or negative. Proper signs have to be used while adding the charges in a system. For example, the total charge of a system containing 5 charges 1, 2, 3, 4 and 5 in some arbitrary units can be plus 1 plus 2 plus minus 3 plus 4 plus minus 5 is equal to minus 1 in the same unit. 1.4.2 Charge is conserved. We have already hinted to the fact that when bodies are charged by rubbing, there is transfer of electrons from one body to the other. No new charges are either created or destroyed. A piece of particle of electric charge enables us to understand the idea of conservation of charge. When we rub two bodies, what one body gains in charge, the other body loses. Within an isolated system consisting of many charged bodies, due to interactions among the bodies, charges may get redistributed, but it is found that the total charge of the isolated system is always conserved. Conservation of charge has been established experimentally. It is not possible to create or destroy net charge carried by any isolated system, although the charge carrying particles may be created or destroyed in a process. Sometimes nature creates charged particles. A neutron turns into a proton and an electron. The proton and electron thus created have equal and opposite charges, and the total charge is 0 before and after the creation. Quantization of charge. Experimentally, it is established that all free charges are integral multiples of basic unit of charge denoted by E. Thus, charge Q on a body always given by Q is equal to NE, where n is an integer, positive or negative. This basic unit of charge is the charge that an electron or proton carries. By convention, the charge on an electron is taken to be negative. Therefore, charge on an electron is taken as minus Z, and that on a proton is plus E. The fact that electric charge is always an integral multiple of E is termed as quantization of charge. There are a large number of situations in physics where certain physical quantities are quantized. The quantization of charge was first suggested by the experimental laws of electrolysis discovered by English experimentalist Faraday. It was experimentally demonstrated by Millikan in 1912. In the International System SI of units, a unit of charge is called a coulomb and is denoted by the symbol capital C. A coulomb is defined in terms of the unit of the electric current, which you are going to learn in subsequent chapter. In terms of this definition, 1 coulomb is the charge flowing through a wire in 1 second if the current is 1 ampere. See chapter 1 of class 11 physics textbook part 1. In this system, the value of basic unit of charges E is equal to 1.602192 into 10 raised to minus 19 coulomb. Thus, there are about 6 into 10 raised to 18 electrons in a charge of minus 1 coulomb. In electrostatics, charges of this large magnitude are seldom encountered, and hence we use smaller units like 1 microcoulomb equal to 10 raised to minus 6 coulomb or 1 millicoulomb equal to 10 raised to minus 3 coulomb. If the protons and electrons are the only basic charges in the universe, all the observable charges have to be integral multiples of E. Thus, if a body contains N1 electrons and N2 protons, the total amount of charge on the body is N2 into E plus N1 into minus E equal to N2 minus N1 into E. Since N1 and N2 are integers, their difference is also an integer. Thus, the charge on any body is always an integral multiple of E and can be increased or decreased also in steps of V. The step size E is however very small because that at the macroscopic level we deal with charges of a few microcoulomb. At this scale, the fact that charges of body can increase or decrease in units of E is not visible. In this respect, the grainy nature of the charge is lost and it appears to be continuous. This situation can be compared with the geometrical concepts of point and lines. A dotted line viewed from a distance appears continuous to us, but it is not continuous in reality. As many points very close to each other normally give an impression of a continuous line, many small charges taken together appear as a continuous charge distribution. At the macroscopic level, one deals with charges that are enormous compared to the magnitude of charge E. Since E is equal to 1.6 into 10 raised to minus 9 coulomb, our charge of magnitude, say 1 microcoulomb, contains something like 10 raised to 13 times the electronic charge. At this scale, the fact that charges can increase or decrease only in the units of E is not very different from saying that charges can take continuous values. Thus, at the macroscopic level, the quantization of charge has no practical consequence and can be ignored. However, at the microscopic level, where the charges involved are of the order of a few tens or hundreds of E, that is, they can be counted, they appear in discrete lumps and quantization of charge cannot be ignored. It is the magnitude of scale involved that is very important. 1.5 Coulomb's law. Coulomb's law is a quantitative statement about the force between 2-point charges. When the linear size of charged bodies are much smaller than the distance separating them, the size may be ignored and the charged bodies are treated as point charges. Coulomb measured the force between 2-point charges and found that it varied inversely as the square of the distance between the charges and was directly proportional to the product of the magnitude of the two charges and acted along the line joining the two charges. Thus, if 2-point charges Q1 and Q2 are separated by a distance r in vacuum, the magnitude of the force F between them is given by F is equal to K into magnitude of Q1 into Q2 magnitude close divided by r square. How did Coulomb arrived at this law from his experiments? Coulomb used a torsion balance for measuring the force between two charged metallic spheres. When the separation between two spheres is much larger than the radius of each sphere, the charged spheres may be regarded as point charges. However, the charges on the spheres were unknown to begin with. How then could he discover a relation like equation above? Coulomb thought of the following simple way. Suppose the charge on a metallic sphere is Q. If the charge is put in contact with an identical uncharged sphere, the charge will spread over the two spheres. By symmetry, the charge on each sphere will be q by 2. Repeating this process, we can get charges q by 2, q by 4, etc. Coulomb varied the distance for a fixed pair of charges and measured the force for different separations. He then varied the charges in pairs, keeping the distance fixed for each pair. Comparing forces for different pairs of charges at different distances, Coulomb arrived at the equation above. Coulomb's law, a simple mathematical statement, was initially experimentally arrived at in the manner described above. While the original experiments established it at a macroscopic scale, it has also been established down to subatomic level, r approximately equal to 10 raised to minus 10 meter. Coulomb discovered his law without knowing the explicit magnitude of the charge. In fact, it is the other way round. Coulomb's law can now be employed to furnish a definition for a unit of charge. In the relation Q, equation 1.1, K is so far arbitrary. We can choose any positive value of K. The choice of K determines the size of the unit of charge. In SI unit, the value of K is about 9 into 10 raised to 9 Newton meter square per Coulomb square. The unit of charge that results from this choice is Coulomb, which we defined earlier in section 1.4. Putting this value of K in equation 1.1, we see that for Q1 is equal to Q2, 1 Coulomb, R is equal to 1 meter, F is equal to 9 into 10 raised to 9 Newton. That is, 1 Coulomb is the charge that when placed at a distance of 1 meter from another charge of the same magnitude in vacuum experiences an electrical force of repulsion of magnitude 9 into 10 raised to 9 Newton. 1 Coulomb is evidently too big a unit to be used. In practice, in electrostatics, one uses smaller units like 1 millicoulomb or 1 microcoulomb. The content K in equation 1.1 is usually put as K is equal to 1 by 4 epsilon 0 for a later convenience, so that Coulomb's law is written as force F is equal to 1 by 4 pi epsilon 0 magnitude of Q1 Q2 divided by R square. Epsilon 0 is called the permittivity of free space. The value of epsilon 0 in SI unit is epsilon 0 is equal to 8.854 into 10 raised to minus 12 Coulomb square Newton raised to minus 1 meter raised to minus 2. Since force is a vector, it is better to write Coulomb's law in the vector notation. Let the position vector of charges Q1 and Q2 be R1 and R2 respectively. See figure 1.3a. We denote force on Q1 due to Q2 by F12 and force on Q2 due to Q1 by F21. The 2 point charges Q1 and Q2 have been numbered 1 and 2 for convenience, and the vector leading from 1 to 2 is denoted by R21. In the same way, the vector leading from 2 to 1 is denoted by R12. R12 is equal to R1 minus R2 equal to minus R21. The magnitude of the vectors R21 and R12 is denoted by R21 and R12 respectively. That is, R12 is equal to R21. The direction of a vector is specified by a unit vector along the vector. To denote the direction from 1 to 2 or from 2 to 1, we define the unit vectors as unit vector R21 is equal to vector R21 divided by magnitude of R21. Unit vector R12 is equal to vector R12 divided by magnitude of vector R12. R21 unit vector is equal to R12 unit vector. Coulomb's force law between 2 point charges Q1 and Q2 located at R1 and R2 is then expressed as F21 is equal to 1 by 4 pi epsilon 0 Q1 Q2 divided by R21 square into unit vector R21. Some remarks on equation 1.3 are relevant. Equation 1.3 is valid only for any sign of Q1 and Q2 whether positive or negative. If Q1 and Q2 are of the same sign, either both positive or both negative, F21 is along unit vector R21 which denotes repulsion, as it should be for like charges. If Q1 and Q2 are of opposite signs, F21 is along minus R21 equal to unit vector R12 which denotes attraction as expected for unlike charges. Thus, we do not have to write separate equations for the cases of like and unlike charges. Equation 1.3 take care of both cases correctly. The force F12 on charge Q1 due to charge Q2 is obtained from equation 1.3 by simply interchanging 1 and 2, that is F12 is equal to 1 by 4 pi epsilon 0 Q1 Q2 divided by R12 square R into unit vector R12 is equal to minus F21. Thus Coulomb's law agrees with the Newton's third law. Coulomb's law gives the force between two charges Q1 and Q2 in vacuum. If the charges are placed in matter or the intervening space has matter, the situation gets complicated due to the presence of charged constituents of matter. We shall consider electrostatics in matter in the next chapter. 1.6 Forces between multiple charges. The mutual electric force between two charges is given by Coulomb's law. How to calculate the force on a charge where there are not one but several charges around? Consider a system of n stationary charges Q1, Q2, Q3, etc. Qn in vacuum. What is the force on Q1 due to Q2, Q3, etc. Qn? Coulomb's law is not enough to answer this question. Recall that forces of mechanical origin add according to the parallelogram law of addition. Is the same true for forces of electrostatic origin? Experimentally, it is verified that forces on any charge due to a number of other charges in the vector sum of all the forces on that charge due to other charges taken one at a time. The individual forces are unaffected due to the presence of other charges. This is termed as principle of superposition. To better understand the concept, consider a system of three charges Q1, Q2, Q3 as shown in figure 1.5a. The force on one charge, say Q1, due to two other charges Q2, Q3 can therefore be obtained by performing a vector addition of the forces due to each other of these charges. Thus, if force on Q1 due to Q2 is denoted by F12, Q12 is given by equation 1.3 given though through other charges are present. Thus, F12 is equal to 1 by 4 pi epsilon 0 Q1 Q2 divided by R12 square into unit vector R12. In the same way, the force on Q1 due to Q3 denoted by F13 is given by F13 is equal to 1 by 4 pi epsilon 0 Q1 Q3 divided by R13 square into unit vector R13, which again is the Coulomb's force on Q1 due to Q3 even though other charge Q2 is present. The total force F1 on Q1 due to two other charges Q2 and Q3 is given as F1 is equal to vector F12 plus vector F13, that is 1 by 4 pi epsilon 0 q1 q2 divided by r12 square into unit vector r12 plus 1 by 4 pi epsilon 0 q1 q3 divided by r13 square into unit vector r13. The above calculation of force can be generalized to a system of charges more than 3 as shown in figure 1.8b. The principle of superposition says that in a system of charges q1, q2, etc. qn, the force on q1 due to q2 is the same as given by Coulomb's law, that is, it is unaffected by the presence of other charges q3, q4, etc. qn. The total force F1 on the charge q1 due to all other charges is given by the vector sum of the forces F12, F13, etc. F1n. That is, F1 is equal to vector F12 plus vector F13 plus etc. plus vector F1n is equal to 1 by 4 pi epsilon 0 whole bracket q1 q2 divided by r12 square into unit vector r12 plus q1 q3 divided by r13 square into unit vector r13 plus etc. plus q1 qn divided by r1n square into unit vector r1n. The vector sum F1 is equal to q1 divided by 4 pi epsilon 0 summation I is equal to 2 to n qi divided by r1i square into unit vector r1i. The vector sum is obtained as usual by the parallelogram law of addition of vectors. All of electrostatics is basically a consequence of Coulomb's law and the superposition principle. 1.7 Electric field. Let us consider a point charge q placed in vacuum at the origin O. If we place another point charge q at a point P where OP is equal to R, then the charge q will exert a force on q as per Coulomb's law. We may ask the question, if charge q is removed, then what is left in the surrounding? Is there nothing? If there is nothing at the point P, then how does a force act when we place the charge q at P? In order to answer such questions, the early scientists introduced the concept of field. According to this, we say that the charge q produces an electric field everywhere in the surrounding when another charge q is brought at some point P. The field there acts on it and produces a force. The electric field produced by the charge q at a point R is given as E of R is equal to 1 by 4 pi epsilon 0 q divided by R square into unit vector R is equal to 1 by 4 pi epsilon 0 q by R square into unit vector R. When R cap is equal to vector R divided by magnitude R is a unit vector from the origin to the point R. Thus, equation 1.6 specifies the value of the electric field for each value of the position vector R. The word field signifies how some distributed quantity, which could be a scalar or a vector, varies with a position. The effect of the charge has been incorporated in the existence of the electric field. We obtain the force F vector exerted by a charge q on a charge q, that is capital Q on a charge small q, as F is equal to 1 by 4 pi epsilon 0 capital Q into small q divided by R square into R cap. Note that the charge q also exerts an equal amount and opposite force on the charge capital Q. The electrostatic force between the charges capital Q and small q can be looked upon as an interaction between charges small q and the electric field of capital Q and vice versa. If we denote the position of charge small q by the vector R, it experiences a force F equal to the charge small q multiplied by the electric field E at the location of q. Thus, F of R is equal to q into capital E of R. Equation 1.8 defines the SI unit of electric field as Newton per Coulomb. Some important remarks may be made here. 1. From equation 1.8 we can infer that if small q is unity, the electric field due to a charge capital Q is numerically equal to the force exerted by it. Thus, the electric field due to a charge q at a point in space may be defined as the force that a unit positive charge would experience if it placed at that point. The charge capital Q which is producing the electric field is called a source charge, and the charge small q which tests the effect of a source charge is called a test charge. Note that the source charge capital Q must remain at its original location. However, if a charge small q is brought at any point around capital Q itself is bound to experience an electrical force due to Q and will tend to move. A way out of this difficulty is to make Q negligibly small. The force F is then negligibly small, but the ratio F by Q is finite and defines the electric field. E is equal to limit Q tends to 0 vector F divided by small q. A practical way to get around the problem of keeping capital Q undisturbed in the presence of small q is to hold capital Q to its location by unspecified forces. This may look strange, but actually this is what happens in practice. When we are considering the electric force on a test charged small q due to a charged planar sheet, section 1.15, the charges on the sheet are held to their location by the forces due to unspecified charge constituents inside the sheet. 2. Note that electric field E due to capital Q, though defined operationally in terms of some test charge small q, is independent of small q. This is because F is proportional to Q, so the ratio F by Q does not depend on small q. The force F on the charge small q due to the charge capital Q depends on the particular location of charge q, which may take any value in the space around the charge capital Q. Thus, the electric field E due to Q capital is also dependent on the space coordinate r. For different positions of the charge small q all over the space, we get different values of electric field E. The field exists at every point in the three-dimensional space. 3. For a positive charge, the electric field will be directed radially outwards from the charge. On the other hand, if the source charge is negative, the electric field vector at each point points radially inwards. 4. Since the magnitude of forces F on charge Q due to charge capital Q depends only on the distance small r of the charge small q from charge capital Q, the magnitude of the electric field E will also depend only on the distance r. Thus, at equal distances from the charge capital Q, the magnitude of its electric field E is same. The magnitude of electric field E due to a point charge is thus same on a sphere with a point charge at its center. In other words, it has spherical symmetry. 1.7.1 Electric field due to a system of charges. Consider a system of charges q1, q2, etc. q1 with position vectors r1, r2, etc. r1 relative to some origin O. Like the electric field at a point in space due to a single charge, electric field at a point in space due to the system of charges is defined to be the force experienced by a unit test charge placed at that point without disturbing the original positions of charges q1, q2, etc. q1. We can use Coulomb's law and the superposition principle to determine this field at a point P denoted by position vector r. Electric field E at R due to Q1 at R1 is given by E1 is equal to 1 by 4 pi epsilon 0 Q1 divided by R1P square into R1P cap, where R1P cap is a unit vector in the direction from Q1 to P and R1P is the distance between Q1 and P. In the same manner, electric field E2 at R due to Q2 at R2 is E2 is equal to 1 by 4 pi epsilon 0 Q2 divided by R2P square into R2P cap, where R2P cap is a unit vector in the direction from Q2 to P and R2P is the distance between Q2 and P. Similarly, expressions hold good for fields E3, E4, etc., En due to charges Q3, Q4, etc., Qn. By the superposition principle, the electric field E at R due to the system of charges is E of R is equal to E1 of R plus E2 of R plus etc. plus En of R is equal to 1 by 4 pi epsilon 0 Q1 divided by R1P square into R1P cap plus 1 by 4 pi epsilon 0 Q2 divided by R2P square into R2P cap plus etc. plus 1 by 4 pi epsilon 0 Qn divided by RNP square into RNP cap. Therefore, electric field of R is equal to 1 by 4 pi epsilon 0 summation I is equal to 1 to n Qi divided by RIP square into RIP cap. E is a vector quantity that varies from one point to another point in space and is determined from the positions of the source charges. 1.7.2 Physical significance of electric field. You may wonder why the notion of electric field has been introduced here at all. After all, for any system of charges, the measurable quantity is the force on a charge, which can be directly determined using Coulomb's law and the superposition principle. Equation 1.5. Why then introduce this intermediate quantity called the electric field? For electrostatics, the concept of electric field is convenient but not really necessary. Electric field is an elegant way of characterizing the electrical environment of a system of charges. Electric field at a point in the space around a charge of system of charges tells you the force a unit positive test charge would experience if placed at that point without disturbing the system. Electric field is a characteristic of the system of charges and is independent of the test charge that you place at a point to determine the field. The term field in physics generally refers to a point charge quantity that is defined at every point in space and may vary from point to point. Electric field is a vector field since force is a vector quantity. The true physical significance of the concept of electric field, however, emerges only when we go beyond electrostatics and deal with the time-dependent electromagnetic phenomena. Suppose we consider the force between two distant charges Q1, Q2 in accelerated motion. Now the greatest speed with which a signal or information can go from one point to another is c, the speed of light. Thus, the effect of any motion of Q1 on Q2 cannot arise instantaneously. There will be some time delay between the effect, force on Q2, and the cause, motion of Q1. It is precisely here that the notion of the electric field, strictly electromagnetic field, is natural and very useful. The field picture is this. The accelerated motion of a charge Q1 produce electromagnetic waves which then propagate with the speed of c, reach Q2 and cause a force on Q2. The notion of field elegantly accounts for the time delay. Thus, even though the electric and magnetic fields can be detected only by their effects, that is, forces on charges, they are regarded as physical entities, not merely mathematical constructs. They have an independent dynamics of their own, that is, they evolve according to laws of their own. They can also transport energy. Thus, a source of time dependent electromagnetic fields turned on for a short interval of time and then switched off leaves behind propagating electromagnetic fields transporting energy. The concept of field was first introduced by Faraday and is now among the central concepts in physics. 1.8 Electric field lines. We have studied electric field in the last section. It is a vector quantity and can be represented as we represent vectors. Let us try to represent E vector due to a point charge pictorially. Let the point charge be placed at the origin. Draw vectors pointing along the direction of the electric field with their lengths proportional to the strength of the field at each point. Since the magnitude of electric field at a point decreases inversely as the square of the distance of that point from the charge, the vector gets shorter as one goes away from the origin, always pointing radially outward. Figure 1.15 shows such a picture. In this figure, each arrow indicates the electric field, that is, the force acting on a unit positive charge placed at the tail of the arrow. Connect the arrows pointing in one direction and the resulting figure represent a field line. Thus, we get many field lines all pointing outward from the point charge. Have we lost the information about the strength of magnitude of the field now? Because it was contained in the length of the arrow? No. Now the magnitude of the field is represented by the density of field lines. E is strong near the charge, so the density of field lines is more near the charge and the lines are closer. Away from the charge, the field gets weaker and the density of the field lines is less, resulting in well separated lines. Another person may draw more lines, but the number of lines is not important. In fact, an infinite number of lines can be drawn in any region. It is the relative density of lines in different regions which is important. We draw the figure on the plane of paper that is in 2 dimensions, but we live in 3 dimensions. So if one wishes to estimate the density of field lines, one has to consider the number of lines per unit cross-sectional area perpendicular to the lines. Since the electric field decreases as the square of the distance from the point charge and the area enclosing the charge increases as the square of the distance, the number of field lines crossing the enclosing area remains constant, whatever may be the distance of the area from the charge. We started by saying that the field lines carry information about the direction of electric field at different points in space. Having drawn a certain set of field lines, the relative density, that is closeness of the field lines at different points, indicate the relative strength of electric field at those points. The field lines crowd where the field is strong and thus spaced apart where it is weak. Figure 1.13 shows a set of field lines. We can imagine two equal and small elements of area placed at points R and S, normal to the field lines there. The number of field lines in our picture cutting the area elements is proportional to the magnitude of field at these points. The picture shows that the field at R is stronger than S. To understand the dependence of the field lines on the area, or rather the solid angle subtended by an area element, let us try to relate the area with the solid angle. A generalization of area to 3 dimensions. Recall how a plane angle is defined in 2 dimensions. Let a small transverse line element delta L be placed at distance r from point O. Then the angle subtended by delta L at O can be approximated as delta theta is equal to delta L by R. Likewise, in 3 dimensions, the solid angle subtended by a small perpendicular plane area delta S at a distance r can be written as delta omega is equal to delta S divided by r square. We know that in a given solid state, the number of radial field lines is the same. In figure 1.13, for 2 points P1 and P2 at distances r1 and r2 from the charge, the elements of area subtending the solid angle delta omega is r1 square delta omega at P1 and at element of area r2 square delta omega at P2 respectively. The number of lines, say n, cutting these area elements are the same. The number of field lines cutting unit area element is therefore n divided by r1 square delta omega at P1 and n divided by r2 square delta omega at P2 respectively. Since n and delta omega are common, the strength of the field clearly has a 1 by r square dependence. The picture of the field lines was invented by Faraday to develop an intuitive non-mathematical way of visualizing electric field around charged configurations. Faraday called them lines of force. This term is somewhat misleading, especially in case of magnetic fields. The more appropriate term is field lines. Lines, electric or magnetic, that we have adopted in this book. Electric field lines are thus a way of pictorially mapping the electric field around a configuration of charge. The electric field line is in general a curve drawn in such a way that the tangent to it at each point is in the direction of the net electric field at that point. An arrow on the curve is obviously necessary to specify the direction of electric field from the 2 possible directions indicated by a tangent to the curve. A field line is a space curve, that is, a curve in 3 dimensions. Shows figure 1.17 the field lines around some simple charge configurations. As mentioned earlier, the field lines are in 3-dimensional space, though the figure shows them only in a plane. The field lines of a single positive charge are radially outward, while those of a single negative charge are radially inward. The field lines around a system of 2 positive charges Q and Q2 give a vivid pictorial description of their mutual repulsion, while those around the configuration of 2 equal and opposite charges Q minus Q, a dipole, shows clearly the mutual attraction between the charges. The field lines shows some important general properties. Field lines start from positive charge and end at negative charges. If there is a single charge, they may start or end at infinity. In a charge-free region, electric field lines can be taken to be continuous curves without any breaks. 3. Two field lines can never cross each other. If they did, the field at the point of intersection will not have a unique direction, which is absurd. Electrostatic field lines do not form any closed loops. This follows from the conservative nature of electric field. Chapter 2. Electric flux. Consider flow of a liquid with velocity v through a small flat surface ds in a direction normal to the surface. The rate of flow of the liquid is given by the volume crossing the area per unit time Vds and represents the flux of liquid flowing across the plane. If the normal to the surface is not parallel to the direction of the flow of the liquid, that is to V, but makes an angle theta with it, the projected area in a space perpendicular to vector V is V ds cos theta. Therefore, the flux going out of the surfaces ds is V into n cap into ds. For the case of electric field, we define an analogous quantity called electric flux. We should, however, note that there is no flow of a physically observable quantity, unlike the case of liquid flow. In the picture of electric field lines described above, we saw that the number of field lines crossing a unit area placed normal to the field at a point is measure of strength of electric field at that point. This means that if we place a small planar element of area delta S normal to E at a point, the number of field lines crossing it is proportional to E delta S. Now, suppose we tilt the area element by angle theta. Clearly, the number of field lines crossing the area element will be smaller. The projection of the area element normal to E is delta cos theta. Thus, the number of field lines crossing delta is proportional to E delta S cos theta. When theta is equal to 90 degree, field lines will be parallel to delta S and will not cross it at all. The orientation of area element and not merely its magnitude is important in many contexts. For example, in a stream, the amount of water flowing through the ring will naturally depend on how you hold the ring. If you hold it normal to the flow, maximum flow through it, and if you hold it with some other orientation. This shows that an area element should be treated as a vector. It has magnitude and also a direction. How to specify the direction of a planar area? Clearly, the normal to the plane specifies the orientation of the plane. Thus, the direction of a planar area vector is along its normal. How to associate a vector to the area of a curved surface? We imagine dividing the surface into a large number of very small area elements. Each small area element may be treated as a planar and a vector across it with it as explained before. Notice one ambiguity here. The direction of an area element is along its normal, but a normal can point in two directions. Which direction do we choose as the direction of vector associated with the area element? This problem is resolved by some convention appropriate to the given context. For the case of a closed curve, this convention is very simple. The vector associated with every area element of a closed surface is taken to be the direction of the outward normal. This is the convention used in figure 1.16. Thus, the area element vector delta S at a point on a closed surface equals delta S into n cap, where delta S is the magnitude of area element and n cap is a unit vector in the direction of outward normal at that point. We now come to the definition of electric flux. Electric flux delta phi through an area element delta S is defined by delta phi is equal to E dot delta S is equal to E delta S cos theta, which as seen before is proportional to the number of field lines cutting the area element. The angle theta here is the angle between E and delta S. For a closed surface with the convention stated already, theta is the angle between E and the outward normal to the area element. Notice we could look at the expression E delta S cos theta in two ways. E into delta S cos theta, that is E times the projection of area normal to E, or E perpendicular to delta S, that is component of E along the normal to the area element times the magnitude of area element. The unit of electric flux is Newton Coulomb inverse meter square. The basic definition of electric flux given by equation 1.11 can be used. In principle, to calculate the total flux through any given surface, all we have to do is to divide the surface into small area elements, calculate the flux at each element and add them up. Thus, the total flux phi through a surface S is phi is equal to summation E dot delta S. The approximation sign is put because the electric field E is taken to be constant over a small area element. This is mathematically exact only when you take the limit delta S tends to 0, and the sum in equation 1.12 is written as an integral. 1.10 Electric dipole. An electric dipole is a pair of equal and opposite point charges q and minus q separated by distance 2a. The line connecting the two charges defines a direction in space. By convention, the direction from negative q to plus q is said to be the direction of the dipole. The midpoint of the locations of minus q and q is called the center of the dipole. The total charge of the electric dipole is obviously 0. This does not mean that the field of the electric dipole is 0. Since the charge q and minus q are separated by some distance, the electric fields due to them when added do not exactly cancel out. However, at distances much larger than the separation of the two charges forming a dipole, that is r very much greater than 2a. The fields due to q and minus q nearly cancel out. The electric field due to a dipole therefore falls off at large distance faster than like 1 by r square. The dependence of r on the field due to single charge q. These qualitative ideas are borne out by the explicit calculations as follow. 1.10.1 The field of an electric dipole. The electric field of the pair of charges minus q and q at any point in space can be found out from Coulomb's law and the superposition principle. The results are simple for the following two cases. 1. When the point is on the dipole axis, and 2. When it is in the equatorial plane of the dipole, that is on a plane perpendicular to the dipole through its center. The electric field at any general point P is obtained by adding the electric fields E minus Q due to charge minus Q and E plus Q due to charge Q by the parallelogram law of vectors. 1. For points on the axis, let the point P be at a distance r from the center of the dipole on the side of the charge Q. E of minus Q is found out, E of plus Q is found out. Then total field at P is found out, and the final answer we get after the derivation is vector E is equal to 4QA divided by 4 pi epsilon 0 r cube into P cap when r very much greater than A. 2. For points on the equatorial plane, magnitudes of the electric fields due to the two charges plus q and minus q are given by E plus q is found out, E minus q is found out. After derivation we get E is equal to minus 1 by 4 pi epsilon 0 2 qa divided by r cube into P cap when r is very much greater than A. From both these equations it is clear that the dipole field at large distances does not involve q and a separately, it depends on the product qa. This suggests that definition of dipole moment. The dipole moment vector P of an electric dipole is defined by P is equal to q into 2a into P cap. That is, it is a vector whose magnitude is charge q times the separation 2a between the pair of charges q and minus q, and the direction is along the line from minus q to plus q. In terms of P, the electric field of a dipole at a large distances takes simple forms. At a point on the dipole axis, E is equal to 2p divided by 4 pi epsilon 0 r cube. At a point on the equatorial plane, E is equal to minus p divided by 4 pi epsilon 0 r cube. Notice the important points that the dipole field at larger distances falls off not as 1 by r square but as 1 by r cube. Further, the magnitude and the directions of the dipole field depends on not only on the distance r but also on the angle between the position vector r and the dipole moment p. We can think of the limit when the dipole size 2a approaches 0. The charge q approaches infinity such a way that the product P is equal to Q into 2A is finite. Such a dipole is referred to as point dipole. For point dipole, equation 1.20 and 1.21 are exact true for any R. 1.10.2 Physical significance of dipoles. In most molecules, the centers of positive charges and negative charges lie at the same place. Therefore, their dipole moments is zero. CO2 and CH4 are of this type of molecules. However, they develop a dipole moment when the electric field is applied. But in some molecules, the centers of negative charge and positive charge do not coincide. Therefore, they have a permanent electric dipole moment even in the absence of electric field. Such molecules are called polar molecules. Water molecules H2O is an example of this type. Various materials give rise to interesting properties and important application in the presence or absence of electric field. 1.11 Dipole in a uniform external field. Consider a permanent dipole of dipole moment P in a uniform external field E as shown in figure 1.22. By permanent dipole we mean that P exists irrespective of E. It has not been induced by electric field. There is a force QE and Q and a force minus QE on minus Q. The net force on the dipole is 0 since E is uniform. However, the charges are separated, so the force acts at the different points, resulting in a torque on the dipole. When the net force is 0, the torque that is coupled is independent of the origin. Its magnitude equals the magnitude of each force multiplied by arm of the couple. Magnitude of torque is equal to QE into 2A sin theta is equal to 2 QAE sin theta. Its direction is normal to the plane of the paper coming out of it. The magnitude of P cross E is also PE sin theta and its direction is normal to the paper coming out of it. Thus, torque is equal to P cross E. This torque will tend to align the dipole with the field E. When P is aligned with E, the torque is 0. What happens if the field is not uniform? In that case, the net force will advently be non-zero. In addition, there will in general be a torque on the system as before. The general case is involved, so let us consider the simpler situations when P is parallel to E or anti-parallel to E. In either case, the net torque is 0. But there is a net force on the dipole if E is not uniform. Figure 1.20 is self-explanatory. It is easily seen that when P is parallel to E, the dipole has a net force in the direction of increasing field. When the P is anti-parallel to E, the net force on the dipole is in the direction of decreasing field. In general, the force depends on the orientation of P with respect to E. This brings us to a common observation in frictional electricity. A comb run through dry hair attracts pieces of paper. Comb, as we know, acquires a charge from the friction, but the paper is not charged. What then explains the attractive force? Taking the clue from preceding discussion, the charged comb polarizes a piece of paper. That is, induce a net dipole moment in the direction of field. Further, electric field due to comb is not uniform. In this situation, it is easily seen that the paper should move in the direction of comb. Continuous charge distribution. 1.12. We have also so far dealt with the charge configuration involving discrete charges Q1, Q2, etc. Q1. One reason why we restrict to discrete charges is that the mathematical treatment is simpler and does not involve calculus. For many purposes, however, it is impractical to work in terms of discrete charges and we need to work with continuous charge distributions. For example, on the surface of a charged conductor, it is impractical to specify the charge distribution in terms of location of the microscopic charge constituents. It is more feasible to consider an area element delta S on the surface of the conductor and specify the charge delta Q on that element. We then define a surface charge density sigma at the area element by sigma is equal to delta Q by delta S. We can do this at different points on the conductor and thus arrive at a continuous function sigma called surface charge density. The surface charge density sigma, so defined, ignores the quantization of charge and the discontinuity in charge distribution at the microscopic level. Sigma represents macroscopic surface charge density, which in a sense is smoothed out average of the microscopic charge density over an area element delta S, which as said before is large microscopically but small macroscopically. The units for sigma are coulomb per meter square. Similar considerations apply for a line charge distribution and a volume charge distribution. The linear charge density lambda over wire is defined by lambda is equal to delta Q by delta L, where delta L is a small line element of wire on the macroscopic scale that however includes a large number of microscopic charged constituents, and delta Q is the charge contained in that line segment. The units for lambda are C by M. The volume charge density, sometimes simply called a charge density, is defined as rho is equal to delta Q by V, where delta Q is the charge included in the macroscopically small volume element delta V that includes a large number of microscopic charges constituents. The units for rho are C by M cube. The notion of continuous charge distribution is similar to that we adopt for continuous mass distribution in mechanics. When we refer to the density of a liquid, we are referring to its macroscopic density. We regard it as a continuous fluid and ignore the discrete molecular constitution. The field due to continuous charge distribution can be obtained in much same way as for system of discrete charges. Suppose a continuous charge distribution in space has charge density rho. Choose any convenient origin O and let the position vector of any point in the charge distribution be R. The charge density rho may vary from point to point, that is, it is a function of R. Divide the charge distribution into small volume element of size delta V. The charge in a volume element delta V is rho into delta V. Now consider any general point V inside or outside distribution with position vector R. Electric field due to the charge P rho delta V is given by Coulomb's law. Delta is equal to 1 by 4 pi epsilon 0 rho delta V instead of sigma divided by R square. Where R is the distance between the charged element P and R cap is a unit vector in the direction of the charged element to P. By the superposition principle, total electric field due to the charge distribution is obtained by summing over electric field due to different volume elements. Therefore, E is equal to approximately 1 by 4 pi epsilon 0 summation all delta V rho delta V by R square. The rho delta V is instead of Q, delta Q. Note that rho R dash R cap dash all can vary from point to point. In a strict mathematical method, we should let delta V tends to 0 and sum then becomes an integral, but we omit the discussion here for simplicity. Using Coulomb's law and the superposition principle, electric field can be determined for any charge distribution, discrete or continuous, or part discrete and part continuous. 1.13 Gauss's law. As a simple application of the notion of electric flux, let us consider the total flux through a sphere of radius r, which encloses a point charge q at its center. Divide the sphere into small area elements as shown in figure 1.25. The figure shows the area element delta S is delta phi is equal to E delta S into is equal to q by 4 pi epsilon 0 r square into r cap into delta S, where we have used Coulomb's law for electric field due to a single charge q. The unit vector r cap is along the radius vector of the center of the area element. Now, since the normal to a sphere at every point is along the radius vector, at that point the area element delta S and r cap have same direction. Therefore, delta phi is equal to q by 4 pi epsilon 0 r square into delta S. Since the magnitude of unit vector is 1, total flux through the sphere is obtained by adding up of flux through all the different elements. That is, phi is equal to summation of all delta S q by 4 pi epsilon 0 r square into delta S. Since each area element of the sphere is at the same distance r from the charge, delta phi is equal to q by 4 pi epsilon 0 r square into delta or summation of all delta S is equal to q by 4 pi epsilon 0 r square into delta S. Now the total area of the sphere equals 4 pi r square, thus phi is equal to q by epsilon 0. Equation 1.30 is a simple illustration of general result in electrostatic called Gauss law. We state Gauss law without proof. Electric flux through a closed surface S is equal to q by epsilon 0, where q is a total charge enclosed by S, and law implies that the total electric flux through closed surface 0 if no charge is enclosed by a surface. We can see that explicitly in the example situation figure 1.23. Here the electric field is uniform and we are considering a closed cylindrical surface with its axis parallel to uniform field E. The total flux phi through the surface is phi is equal to phi 1 plus phi 2 plus phi 3, where phi 1 and phi 2 represent the flux through the surfaces 1 and 2 of circular cross section of the cylinder, and phi 3 is the flux through the curved cylindrical part of the closed surface. Now the normal to surface 3 at every point perpendicular to E. So by definition of flux, phi 3 is equal to 0. Further, outward normal to 2 is along E, while the outward normal to 1 is opposite to E. Therefore, phi 1 is equal to minus S into S minus E into S1. S1 is equal to S2 is equal to S3. S2 is equal to E into S2. Phi 2 is equal to plus E into S2. Whereas is the area of circular cross section, the total flux is 0 as expected from Gauss law. Thus, whenever you find that the net electric flux through a closed surface is 0, we conclude that the total charge contained in the closed surface is 0. The great significance of Gauss law equation 1.31 is that it is true that in general and not only for the simple cases we have considered above. Let us note some important points regarding this law. 1. Gauss law is true for any closed surface no matter what its shape or size. Term Q on the right side of Gauss law includes that sum of all charges enclosed by the surface. The charge may be located anywhere inside the surface. 3. In the situation when the surface is so chosen that there are some charges inside and some outside, electric field whose flux appear on the left side of equation is due to all the charges, both inside and outside S. In term Q On the right side of the Gauss law, however, represents only the total charge inside the S. 4. The surface that we choose for the application of Gauss law is called the Gaussian surface. You may choose any Gaussian surface and apply Gauss law. However, take care not to let the Gaussian surface pass through any discrete charge. This is because electric field due to a system of discrete charges not well defined at the location of any charge. As you go close to the charge, field grows without any bound. However, the Gaussian surface can pass through a continuous charge distribution. 5. Gauss law is often useful towards a much lesser calculation of the electrostatic field when system has some symmetry. This is fascinated by the choice of suitable Gaussian surface. Finally, 6. Gauss law is based on the inverse square dependence of distance contained in the Coulomb's law. Any violation of Gauss law will indicate departure from inverse square law. Applications of Gauss law. 1.14.1 Field due to an infinitely long straight uniformly charged wire. Consider an infinitely long thin straight wire with uniform linear charge density lambda. The wire is obviously an axis of symmetry. Suppose we take the radial vector from O to P and rotate it around the wire. The point P, P dash, P double dash so obtained are completely equivalent with respect to charged wire. This implies that the electric field must have the same magnitude at these points. The direction of electric field at every point must be radial, outward if lambda greater than 0, inward if lambda less than 0. This is clear from figure 1.26. Consider a pair of lines elements P1 and P2 of the wire as shown. The electric field produced by the two elements of the pair when summed gives a resultant electric field which is radial. The components normal to the radial vector cancel. This is true for any such pair, and hence the total field at any point P is radial. Finally, since the wire is infinite, electric field does not depend on the position of P along the line of the wire. In short, the electric field is everywhere radial in the plane cutting the wire normally, and its magnitude depends only on the radial distance r. To calculate the field, imagine a cylindrical Gaussian surface as shown in figure 1.26b. Since the field is everywhere radial, flux through the two ends of the cylindrical Gaussian surface is 0. At the cylindrical part of the surface, E is normal to the surface at every point, and its magnitude is constant since it depends only on r. The surface area of the curved parts is 2 pi rl, where L is the length of the cylinder. Flux through Gaussian surface is equal to flux through the curved cylindrical part of the surface equal to E into 2 pi rl, where 2 pi rl is the surface area. The surface includes charge equal to pi L. Gauss law then gives E is equal to 2 pi rl is equal to pi L by epsilon 0. That is, E is equal to lambda divided by 2 pi epsilon 0 into r. Vectorly, E at any point is given by E is equal to lambda by 2 pi epsilon 0 into r into n cap, where n cap is the radial unit vector in the plane normal to the wire passing through the point. E is directed towards lambda is positive and inwards if lambda is negative. Note that when we write a vector A as a scalar multiple by unit vector, that is as A is equal to A cap, scalar A is an algebraic number. It can be negative or positive. The direction of A will be same as that of the unit vector A cap if A greater than 0 and opposite to A cap if A less than 0. When we want to restrict non-negative values, we use symbol mod A and call it the modulus of A. Thus, modulus of A greater than or equal to 0. Also note that though only the charge enclosed by the surface 2 pi L was included above. The electric field is due to the charge on the entire wire. Further, the assumption that the wire is infinitely long is crucial. Without this assumption, we cannot take E to be normal to the surface part of the cylindrical Gaussian surface. However, equation 1.32 is approximately true for electric field around the central portions of long wire, where the end effects may be ignored. Field due to a uniformly charged infinite plane sheet. Let sigma be the uniform surface charge density of an infinite plane sheet, figure 1.27. We take the x-axis normal to the given plane. By symmetry, the electric field will not depend on y and z coordinates, and its direction at every point must be parallel to the x direction. We can take the Gaussian surface to be a rectangular parallel piped off cross section area A as shown. A cylindrical surface will also do. As seen from the figure, only the two faces 1 and 2 will be contributing to the flux. Electric field lines are parallel to the other faces, and they therefore do not contribute to the total flux. Unit vector normal to the surface 1 in minus x direction, while the unit vector normal to the surface 2 in the positive x direction. Therefore, flux E delta S through both the surfaces are equal and are added up. Therefore, the net flux through the Gaussian surface is 2 into E into A. The charge enclosed by the closed surface is sigma into A. Therefore, by Gauss law, 2E is equal to sigma A by epsilon 0, or E is equal to sigma by 2 epsilon 0. E is equal to sigma by 2 epsilon 0 into n cap vectorically, where n cap is unit vector normal to the plane and going away from it. E is directed away from the plate if sigma is positive, and towards the plate sigma is a negative. Note that the above application of the Gauss law has brought out an additional fact that E is independent of x also. For finite large planar sheet is approximately true in the middle region of the planar region away from the ends. 1.14.3 Fields due to uniformly charged thin spherical shell. Let sigma be the uniform surface charge density of thin spherical shell of radius r. Situation as obvious spherical symmetry. The field at any point P outside or inside can depend only on r, the radial distance from the center of the shell to the point, and must be radial, that is along the radius vector. 1. Field outside the shell. Consider a point P outside the shell with the radius vector r. To calculate E at P, we take the Gaussian surface to be a sphere of radius r and with the center O passing through P. All points on this sphere are equivalent related to given charge configuration. That is what we mean by spherical symmetry. The electric field at each point of the Gaussian surface therefore has the same magnitude E and is along the radius vector at each point. Thus, E and delta is at every point are parallel, and flux through each element is E delta S. Summing over all delta S, the flux through the Gaussian surface is E into 4 pi r square. The charge enclosed is sigma into 4 pi r square. By Gauss law, E into 4 pi r square is equal to sigma by epsilon 0 4 pi r square, or E is equal to sigma r square divided by epsilon 0 r square is equal to Q by 4 pi epsilon 0 r square, where Q is equal to 4 pi r square. Sigma is the total charge on the spherical surface. Vectorially, E is equal to 1 by 4 pi epsilon 0 Q by r square into r cap. The electrical field is directed outward if Q greater than 0 and inward if Q less than 0. Thus, however, is exactly the field produced by a charge Q placed at the center O. Thus, for points outside the shell, the field due to a uniformly charged shell is as if the entire charge of the shell is concentrated at its center. field inside the shell. In figure 1.28b, the point P inside the shell, Gaussian surface is again a sphere through P centered at O. The flux through the Gaussian surface, calculated as before, is E into 4 pi r square. However, in this case, Gaussian surface encloses no charge. Gauss law then gives E into 4 pi r square is equal to 0. That is, E is equal to 0. That is, the field due to uniformly charged thin shell is 0 at all points inside the shell. This important result is a direct consequence of Gauss law, which follows the Coulomb's law. Experimental verification of this result confirms the 1 by r square dependence in the Coulomb's law. So that's all for this chapter. Please do subscribe this channel for more content, and please do support us. Thanks for watching, and thank you. And do comment your responses in the comment section below so that I can understand what all changes I have to make in my content. Thanks.